all those electrons move around when we do these diagrams, right? All the electrons move around. Why do they move around? Well, why? To achieve noble gas electron configuration. That's why the electrons move around. But notice I asked why the electrons move around. Now I'm going to ask a different question. Why does it stick together? Opposite charges attract. So the reason why they move electrons is not why they stick together. They move electrons to look like noble gases. Once they look like noble gases, they stick together because they have opposite charges. So the bond is actually the opposite charges. It's not the electrons moving. The electrons make the ions. Once you got the ions, the opposite charges hold them together. So the reason why they stick together is not because to reach noble gas configuration. They reach noble gas configuration and then they stick together. Okay, that's the bond. The bond is opposites attract. Oh, we're back to that saying again? Yeah, it's a pretty big idea for this whole thing. Opposites attract. More opposites attract more. Okay. Now the most common ionic compound we talk about is salt. But it's not actually salt, it's just a salt. Because all ionic compounds are salts. If they want to be specific, they should say table salt. Okay. Any solid ionic compound is called a salt. So you may see it as Epsom salts. Baking soda is a salt. Okay. If it's got a metal and a non-metal in it, it's a salt. Because that's what it takes. You've got to have a metal and a non-metal. And here's where people have lied to you in the past. Okay? As I know they do it all the time. They say that the smallest piece of an element is an atom. And the smallest piece of a compound is a molecule. You heard that before? It's wrong. Okay? Smallest piece of an atom, the smallest piece of an element is an atom. But the smallest piece of a compound is only sometimes a molecule. Because a molecule means that this atom is stuck to that atom. And they stay together all the time. Ionic compounds don't do that. I got all those ions. Now that I drew those pictures, can you tell which electrons went from which atom to the other? No, all I show you is this. No, so when you get the ions, you can't tell where the electrons came from. Okay? They just stick together because of opposite charges. That's not a molecule. That's not a molecule. A molecule means this atom reacted with that atom. And they're still hooked to each other. These just stick to each other because of opposite charges, so I make a big pile of it. They just arrange themselves at opposite charges. You can't even tell that the atom that you gave your electron to is even next to you. Okay? When it's all said and done, you can't even guarantee it's going to be next to you. Whereas if I say H2O, that H is hooked to that O. Okay? That's the difference. So the word is not molecule, it's formula unit. Because all it really is where they equal 0. That's all it is where they're neutral. That ratio. That smallest piece. So the smallest piece of an ionic compound is a formula unit. So if it's got a metal in it, that means it's got a metal and a nonmetal. That means it's ionic. That means that the piece is going to be a formula unit, not a molecule. Okay? Sometimes you'll say the bond is formed through the transfer of electrons. That's a different way of looking at it, right? Okay, the bond is formed, actually it's formed after they transfer electrons because they transfer electrons to achieve noble gas electron configuration. change that word. Oh, sorry. I like a better word. Better word, not through. After transfer electrons.
How are noble gases first found again?
They were first found by cooling air because they didn't react with anything. That turns out that about 0.5% of our air is argon. Okay. So they just cooled the air and got rid of the stuff they knew, and we're still left over with stuff. Okay. So this is one way atoms can bond. Okay. There's another way. Covalent bonding. So the second way they form is by covalent bonding. So let's go back to it. Go to basic. Why do compounds form? You choose noble gas configuration because it's lowest energy, right? So the reason why noble gas is because it's low energy. If the bowling ball falls in a hole, it's going to stay there. The lower the energy, the longer it stays there. Okay. Okay. So we had a last kind of bond. We had a metal which could give away an electron, and a non-metal which could take an electron, so that they could both end up looking like noble gases. But what if I put two non-metals together? They both want more electrons, and neither one will give away an electron. They can't do this. Because you got all takers, no givers. But there's a way around it. There's a way around it. They share their valence electrons. And that's why the word covalent. Co, together. Valent, valence electrons. Their valence electrons are together. Covalent. So sharing electrons is a covalent bond. And when they share, they both get to count those electrons they share towards their noble gas configuration. So if you come to my house and ask me, how many cars do you have? I'd say 2. If you ask my wife, how many cars we have? She'll say 2. Ask my son how many cars we have. He'll say 2. Do we have 6 cars? No, we count the ones we share. Okay, the same thing's going to happen here. They're going to count the ones they share. Okay. Now, covalent bonding actually makes molecules. This is the kind that makes molecules. By molecules, we mean specific atoms that are joined by sharing electrons. Now, so the H is hooked to the O in water. And you note they're sharing those specific electrons. And there's 2 kinds of molecules. 2 ways you can make molecules. You can make a molecular compound when different elements share electrons. When hydrogen and oxygen share electrons. The second option is the second place that kind of misled you. They said the smallest piece of an element is an atom. And while that's true, for most, there's a group of elements that you never find alone. The air we breathe, the oxygen in the air we breathe is not O. It's O2. Okay. Those are diatomic molecules. 2 of the same atom. The nitrogen in the air is not N, it's N2. there's a group of atoms we never find by themselves. So technically the atom is the smallest piece, but you can never find that in nature. You have to separate the two from each other. So the oxygen we breathe is O2, the nitrogen in the air is N2, the hydrogen that burns is H2, but helium is He. It doesn't get a 2. Why would it? Helium is a noble gas. Well, how many electrons would it have to share to get to noble gas configuration? None. Okay. So they're made of just nonmetals or nonmetals and hydrogen. Hydrogen is, well, it's not in the metalloid, can sometimes act like a metal, sometimes act like a nonmetal. For right now, I have to tell you, eventually there's a way you'll be able to tell. Now, molecules, these things tend to have low melting and boiling points. What I mean by that is, anything that you have ever seen as a liquid, or anything that you have ever seen as a gas, is either an element or a molecular compound. I don't think you've ever seen a melted ionic compound. Every time you see an ionic compound, it's either a solid or dissolved in water. Okay? If you wanted to melt table salt and you put it in an iron pan and put it on your stove, it would be a race to see which melted first, the pan or the salt. And your stove wouldn't work because it doesn't get hot enough to melt either one of them. To melt the iron, you only have to get up to 1800 Kelvin, which is 1500 Celsius. Salt, I think its melting point is about 2000 Celsius. Okay? So, if you've seen it as a liquid or a solid, a liquid or a gas, it's molecular. Okay? I will actually get a chance to show you a melted ionic compound. Okay. And they're going to have a formula. I mean, we've written the formulas before. Here we could do it, Al2S3, right? 2 Als, 3 Al3S2, Al2S3, Al2S3. But wouldn't this have also worked if I'd done 4 aluminums and 6 sulfurs? Right? If I doubled everything, wouldn't it still work? Okay. But I don't write I wouldn't write Al4S6 because that's not the lowest ratio, right? Okay. Thing is, with molecular compounds, they are not the lowest ratio. They don't have to be the lowest ratio. Because you're not just held together by charges, you're actually sticking atoms together. I mean, the molecule you talked most about last year, glucose. That is the molecule you talked most about last year, right? All right. Okay. C6H12O6. Is that the lowest ratio? No. Those are all divisible by 2, aren't they? But the real molecule has 6 carbons, 12 hydrogens, and 6 oxygens. Okay? There's not a lowest ratio for this one. I can't just simplify it and say, oh, because I have to have specific atoms joined. Think about what the formula would be for something like DNA, where it's got millions of atoms. DNA is one molecule. Okay? The formula doesn't tell you where the carbons are, or the hydrogens, or the oxygen. You can't tell from this whether the carbon is hooked to the hydrogen or the carbon is hooked to the oxygen. You can't tell for sure. let's show you how it works. Okay, so they're nonmetals. They hold on to their valence electrons. They can't give away electrons to bond, but they still need that noble gas configuration. And we get it by sharing. And the ones they share, they both get to count. Okay? Let's see what it looks like. And I'll start off with a diatomic molecule. So we don't have to work too hard. We're talking about F2. Fluorine is diatomic. Okay, so fluorine has 7 valence electrons. Are you okay with that? So I can draw fluorine. A second fluorine also has 7 dots. Right? And when I put that second one there, and I put them next to each other, and they share these electrons here, how many electrons are around that? How many outside electrons are around that fluorine? 8. A stable octet. How many are around this one? 8. They both end up with full orbitals. Because you get to count these electrons twice. Once for each atom. Does that make sense? So these both look like noble gases. So they look like noble gases. Right? By sharing. See how this is completely different than the ionic we just did. In ionic, the electrons moved and then the charges stuck together. Okay? First they got noble gas configuration, then they stuck together. Here, they don't get noble gas configuration until they stick together. And if you tear them apart, they don't have noble gas configuration anymore. Whereas if I could tear these apart, they'd still have noble gas configuration. Make sense? Okay. So what we drew right here, yeah. Because they're already charges. So if I melt the solid aluminum sulfide, the Al3 plus and the S2 minus can move around separately. But if I melt F2, the F's have to stay together the whole time. That's the difference between a molecule and a formula unit. When I melt it, the F's stay together. When I melt this S can go away from that Al. Notice these are big charges, right? It's hard to tear them apart. That's why they have really high melting points. Okay. So a single covalent bond, a sharing of 2 valence electrons, or a pair of valence electrons. Watch the wording in the questions, because sometimes they ask for how many electrons are shared, and sometimes they ask for how many pairs of electrons are shared. Watch that wording. Okay. I've seen people fall for that one before. They ask you for electrons or pairs of electrons. Okay. Again, it's only nonmetals and hydrogen. Okay. So, how to show how they formed. Okay. It's like a jigsaw puzzle. What is the most useful part of a jigsaw puzzle? Edges, sides, corners? Nah. The picture on the box is the most useful part of a jigsaw puzzle. Everybody in agreement? You want to know what it looks like when it's done. Well, I have to tell you that, because I can't tell you put carbon, hydrogen, and oxygen together, because you don't know how many carbons, how many hydrogen, because there are millions of ways to put carbon, hydrogen, and oxygens together. Millions of ways. So I got to be specific about which one I want. I got to show you the picture on the box. Okay? So all you see, and that's different here. Here, I didn't have to tell you 2 aluminums and 3 sulfurs. You could figure it out. But here I have to tell you. Okay? And all you have to do is put the pieces together to end up with the right formula. So the one covalent bond we talk about most often is water. Let's show how water is formed. How H2O sticks together. What does a molecule of water look like? How are the atoms connected? So, water. I got to worry about, and the formula for water is H2O. Our puzzle has to look like H2O. So I look at the H. It gets 1 dot. Okay. Second way, another way you want to look at this is not only does hydrogen have 1 dot, it has 1 hole. It wants 1 more electron. It's got a hole to fill. Because with 2, hydrogen looks like helium, and it's done. The oxygen has 6 valence electrons, but another way to look at it, it's got 2 holes. And we're going to shorten noble gas electron configuration a little bit. We're going to call it happy. Make them happy. By happy, we mean noble gas electron configuration. On a test, you can't answer happy. You got to answer noble gas configuration. Because you're not just writing for me down the line. You got to write for other people. Other people are not going to understand happy. Actually, if they're chemists, they probably will, but they won't give you credit. They'll probably understand it. They just won't give you credit. Okay. So there's my pieces. I got an H. I got an O. Can you see where the H could hook onto the O? Yeah, I just push them together. Now, if you look carefully, this hydrogen has 2 dots next to it. It's happy. Okay. The oxygen is not happy. There's only 7 dots. It's a good thing the formula for water is not HO. The formula for water is H2O. So I got another H. Another H has another dot. Can you see where the other H could fit in? And do you see why I said the rule for writing dots is don't pair them up until you have to. You can put them on any side. Because I need to move that H to the top so I can stick it in there. You ever see why I move my dot? Okay. So you understand why that's better than clockwise. Clockwise, your openings will always be on the same side. And you can never put 2 things together. That makes sense? So I push that H together. And everybody's got a noble gas configuration. There's 8 around oxygen. And there's 2 next to each hydrogen. So they're all following the octet rule. Remember, octet rule doesn't mean 8. It means looks like noble gas. So hydrogen with 2 is following the octet rule. Sounds kind of wrong when you know the prefix oct means 8. Okay, so that's how you do it. Let's try a few. Yeah.
If metals are losers,
Yep.
then hydrogen would have 0 electrons.
That's right. I think I went into that hydrogen loses its electron when it forms a +1 ion, and that's what makes it dangerous. Because it's small, tiny, because it's just a proton, and it's positive. So it's a small piece with a charge, which means small piece isn't getting close. With a charge means it can yank. And that's what makes acids dangerous. All right. Everybody okay with that? Yeah.
Is it hard to access a single hydrogen?
The scientists have techniques to trap individual atoms so they can work with them one at a time, so they learn how that individual atom's working. But we'll work on a bigger bulk scale. We want to know if we understand how one works, then we really understand how all of them work. So they can manipulate individual atoms now. I've seen they draw pictures with atoms. where they actually build a little snowman out of atoms by manipulating individual atoms. There's a place, there's a factory on 4th Street where they do precision glass. They make the lenses for satellites, that type of high-end glass. So that to check how smooth their glass is, they use something called an atomic force microscope that notices if there's an atom too big to make it rough. That's how you get really smooth glass. Okay? So yeah, that's nanotechnology, manipulating individual atoms. So when you hear about nanotechnology, that's what they're able to do, is pick one atom and say, I want to do this with it. Question?
What types of acid?
There's lots of different kinds of acids because there's, I would say, tens of thousands. Tens of thousands. Acids is a big category because a lot of our organic materials are acids. I mean, the taste of vinegar is an acid. The sour and lemon's an acid. Okay, so let's try a couple more of these. Show me how H and I could make HI. Now I'm going to color code my dots so I can see where they come from, but it really doesn't matter where they come from. But just so you can see the process, I'll change my colors. So my H has 1 dot, and my O, my I, has 7. So 1, 2, 3, 4, 5, 6, 7. Does everybody look like a noble gas? Have I added any electrons? Nope. I started off with 1 for hydrogen and 7 for iodine, and I got 8. I got 8 dots there. So I've got the right atoms with the right number of dots, and everybody looks like a noble gas. I'm done. Hmm? How about PCl3? Draw my phosphorus with its 5 dots. Okay, and I have to hook on some CLs. So CL's chlorine. It's got 7 dots. Can you see where to hook on a chlorine? How about here? Would that work? Because it's got 1, 2, 3, 4, 5, 6, 7. Hey, that chlorine's happy now. It's got 8 dots around it. But we're not done yet. The phosphorus isn't happy, and I've only done 1 of my 3 chlorines. So I put the second one on. 1, 2, 3, 4, 5, 6, 7. And the third one on. 1, 2, 3, 4, 5, 6, 7. I put in all my dots. Everybody's got 8 electrons around them. Everybody's happy? Say, well, Mr. Green, this is really easy. Just fill the holes. It's not always this easy. I've given you this is the basic technique, but you can make it more complicated really simple. We know water is H2O. Hydrogen peroxide is H2O2. H2O2, hydrogen peroxide. That's its formula, H2O2. Try it. Well, the H has got 1 dot and the O has got 6. Now, when I see this H with 1 dot and see it only has 1 hole to fill, to me, that tells me it's a dead end. That wherever I put that H, I'm done in that direction. because it can't make another bond. See how that one dot tells me it's a dead end? Okay. I use this analogy and I checked with somebody with one arm and they said it was okay. Okay. Why, if you've only got one dot, you can't be in the middle. Because if you're playing a game of Red Rover, you do not want the one-armed person in the middle. They need to be at the end of the line. Everybody agree? Okay. So we've got those guiding principles. So we start off, we've done this before. I take my O, I draw 6 dots, and then I hook on an H with its dot, and an H with its dot. Everybody's happy, we're done. No, we're not done. I got everybody full, but I got to put another O on. Right? So apparently, adding both hydrogens was the bad choice because those hydrogens are dead ends. I got no place to hook on my oxygens. So if I'm going to run into that problem of dead ends, I probably don't want to start off by hooking the hydrogens on because the hydrogens are dead ends. I should probably start with the oxygens because the oxygens are going to have to hook to each other. Right? Because the two H's are dead ends. So that doesn't work. So the two oxygens have to hook onto each other. It's the only way it's going to work. Everybody get that? Okay. So then I can hook the H on here, and I can hook an H on here, and everybody's happy. Does that make sense? It's a puzzle. It really is a jigsaw puzzle. They always go together. Okay? Won't give you one that doesn't go together. I mean, what happens when you throw a third kind of atom in there? What if I ask you to do CH4O? Okay, so I got carbon with 4 dots, hydrogen with 1 dot, and oxygen with 6 dots. That's what I have to work with. Did we learn something with our last one? Don't start off with hydrogen, right? And actually, hydrogen's not the only one you're not going to want to start off with. You also wouldn't want to start off with fluorine. Everybody see why you wouldn't want to start off with fluorine? It's a dead end. It's only got one hole to fill, right? It's a dead end. Actually, all the halogens are going to be like that. But so if I'm not going to start off with the hydrogen, then I got to stick the carbon and oxygen together. Okay. That's the C and the O. And the H comes in here. An H comes in here. An H comes in here. That's 3. And the 4th one goes over here. Okay? Don't start with H's. Actually, nobody writes the formula this way. The way this formula is written, they write
because of the configuration.
CH3OH. Now, and actually, it's not so much the configuration, but this right here In your functional groups back in biology, everything that ended in OH was an alcohol. When you talk about your macromolecules, there were acids, there were alcohols, just an alcohol. There are amines. So you know what? He remembers the little bit of chemistry I was supposed to learn in biology last year. Yeah. So they're focusing on this piece. So if they have that piece hooked to nonmetals, they always write it off that way. Okay. How about BA and S? So I put the BA with its 2 dots next to the S with its 6. Oh, that one too many on this S. Is there any way for me to make everybody have an octet here?
Nah,
Well, why? Why can't I do this?
because that's like not how it works.
Because barium's a metal and sulfur's a nonmetal. They don't covalently bond. To show how barium and sulfur form, first decision is, what kind of compound do you have? Barium gives its electrons to sulfur.
So ionic.
It's an ionic one. We got 2 ways to make bonds. The first thing you should decide is, which way are they doing it? This is where we started today, right? We knew how to do that. We learned a new technique. Doesn't mean we get to forget the old one. We got to make a choice about which way it happens. And the big distinction, how do you make that decision? Your friend is the zigzag line. Because if it's got a metal in it, it's ionic. Everybody okay with that? It's got a metal in it, it's ionic. Yeah.
How do you know if it's like a metal with a metalloid?
On a metalloid, we'll have to tell you, or actually, if you put a metal with a metalloid, the metalloid acts like a nonmetal. If you put a nonmetal with a metalloid, the metalloid acts like a metal. Yeah. And so, did they clear this, or oh, they put the X on? Okay, thanks.
Literally, it's like